So for this case, they want us to determine the position of the center of mass. Steel plate is 0.3 thick and has density of that value. Determine the location of its center of mass. Okay, so if we're going to get the center of mass for something like this, how are we going to do it? So the center of mass will also have coordinates x bar, comma y bar. So this is how we're going to obtain the center of mass. So we need to find x bar, we need to find y bar. So the formulas here that we're using are similar to the ones we used for center of the centroid of an area and so on. So those are going to be similar. And since this actually has some form of thickness, we can actually look at its center of mass not only to be x comma y. We can also give it a third variable since because of that thickness. So I can say comma z bar. Do you get my reasoning there? So the third variable is only coming in because of the thickness in question there. If it is something thin, we assume everything is literally on a plane, on a sheet. So only have x bar, comma y bar. So here we're kind of assuming this is actually a volume because of that thickness being mentioned. So, but of course, to get z, it's just going to be halfway of the thickness. So that is not going to be a problem there. So the z bar, because of it's just the thickness there, is just going to be the thickness divided by 2. So this is going to be an easy 0.15. But we need to get x bar, comma y bar. So now we're going to treat this as a plane, a thin lamina. And how are we going to find its center of mass? So mathematically, we have the same formulas we had under as in under center of the centroid. We have x tilde. Since it is the center of mass, this is going to be dm over. Then here we have dm. Now we need to pick a differential mass that we're going to use. And that's the one that we're going to take advantage of. You can go with these formulas and see how we can extend them to show how they will reduce, or you can use the formulas that you had in math. Do you remember the formulas you had for center of mass in math? Okay. So here we have to determine what dm is, and we also have to determine what x tilde and what y tilde is. So we need to figure out what those two are. Once we have those, it becomes easy for us to actually work this problem out. So we are still going to use strips to determine the center of mass. So here is what we need. Because we've been given density, we know that density is equals to mass over volume. So that is what we know. Okay, so we can extend this if we wanted the density of an area. And this when you look at this is for mass over volume. That's for a thickness. So if we pick a strip like this, for example, if we pick a strip like this, so this strip can be viewed as something like this. And the thickness is somewhere this side. So the top part is controlled by y squared is equals to 2x. The bottom part is controlled by y is equals to minus x. And notice that as this strip moves through from here all the way up to the far end, it doesn't really change. Everything remains the same. The top remains the top, the bottom remains the bottom. So we want to get the expression for the mass and for the volume. So for this strip, when you look at it, since what we're dealing with is not the full, it's not the full shape, we're looking at it basically as a small piece. We can look at its volume in terms of a differential volume and then correspondingly a differential mass. So its density can now be viewed as the differential mass over the differential volume. So this is what we end up having. So now we get dm to be equal to the density multiplying the dv. So we now have an expression that is going to go where we have dm, but still we're thinking this dv, we don't really want to have dv there. We don't want to integrate with respect to the volume. Can we have something better there since the thickness is actually a constant? So the thickness is a constant, meaning this part can be seen as just a number. This part from here to there in the z-axis, that is just a 0.3. So in the z-axis, what we have there is a 0.3. So the only thickness that we are not sure of is this one here in the x-axis, this one here. So this in the x-axis, we can take it as a dx. While on the other side, we have a 0.3. The height, however, is changing from negative x all the way up to 2x. So not to 2x, we can write this as y is equals to root of 2x. So the height is changing. We can write it as the top, which is root of 2x, minus negative x, which makes this a plus x. That is going to be our height. From there, notice that we can then obtain the expression for the volume. Since it's the volume of a section, so this is dv. So dv becomes equal to the height, which is root of 2x plus x. That is just the height. Let's copy this. So that's question 6. So I hope you're seeing how that is turning out. Okay, so we were somewhere here. So we're trying to get the expression for dv. We're going to multiply, since its volume is going to be lbh. The height is here, the h. Now we need the thickness there. The thickness is a dx, so we're going to have times dx. Then lastly, the width there, that thickness of the lamina, which is 0.3. So now our dv has turned out to be 0.3 root 2x plus x multiplying dx. This is what our dv has turned out. So meaning dm will now be equal to the density. Since remember, dm is this density times dv. So dm now is going to be equal to the density times 0.3 root of 2x plus x dx. So this is our dm. Any questions here? Okay. Once we have obtained our dm, we can then go to our formula. Remember we said x bar will be equal to x tilde. So all we need there is now x tilde for this section. So since we have selected a vertical section, what will be the position of the x coordinate? So we pick a point that lies somewhere on the curves, on the boundaries. So you can pick a point that lies, we can pick one on top, one at the bottom. So one can be said to be here, x, comma, y2. Since the values of y will be different, but for these 2 points, the values of x will be the same. This will be the same x, comma, y1. So the centroid for this point, for this setup, let's say for this small section you have picked, let's say to be somewhere slightly here. Its x value, notice that its x value will be similar to the x value at those points on the boundaries. So the x values will be the same, x. So we're saying that x tilde will be the same as just x. Y tilde, however, will be different. Y tilde, if you recall, we did show you how to get the midpoint between two values. Y tilde will need to add the lower value of y plus the upper value of y divided by 2. This will give us the exact midpoint between the two values of y. That will be our y tilde. But let's substitute what y1 is. y1 is the value of y at the bottom, and the value of y here will be given by negative x. So here we'll have minus x. At the top, the value of y, when you make y subject, it will be root of 2x. So this will be plus root of 2x. So this will have to be divided by 2. This will be the expression that gives us y tilde. So we can go back to our integral. We need x tilde. So where there's x tilde, we saw x tilde is the same as just x. Then we need dm. dm is the density times 0.3. Then we have root of 2x plus x dx. Then this will be divided by root of dm. Again, dm comes with density times 0.3 root of x, root of 2x, I mean, plus x. Here you see that density is a constant. If the density is uniform, and I think that's the case we are looking at, most of the questions you'll be given, you'll be dealing with uniform density. So if we are assuming this is made of uniform density, so it has a density of this, I haven't said anything about the density changing, so we're going to assume that is a uniform density. So if the density is uniform, meaning it can be factored out above, or it's just a number which has been given there. So being a number that is a constant, it will not be affected by the integral. So we can factor it or remove it from the integral sign. So you see that you have, I can basically get the 0.3 as well. And then here we now just have x root of 2x plus x. Wait, where is this x coming from? So, oh yeah, this x here. So I think I literally thought it was a multiplication now. So you have x, and then we have this dx. In the denominator, we also have the density and the 0.3. So you have 0.3 in that density. Plus the x there again. Clearly, the 0.3 in density will cancel out. This is why in most cases, you would not even need to have that density there because it always cancels out. So in the end, we are just integrating I can write this as x. The root 2x, I can write it as root 2 and root x separately. Then plus x there. Because I'm integrating with respect to x, I might as well figure out the limits first. So the limits, because we're going with dx, they're going to be values of x, from the smallest value of x to the largest value of x. So where are they? So when you look at this setup here, what is the smallest value of x? Pardon? Pardon. 0. And what's the largest value of x? 2. Yes. So we're changing from 0 to 2. So we can distribute the integral sign with that x there. The first term in the numerator, the root 2 can come out. So we just have x multiplying root of x. Root of x can be seen as x to the power half. The second term, when x multiplies, we get x squared. So this will be x squared from 0 to 2. I've just distributed the integral sign with that. When it comes here, the root 2 can come out. The x from outside is this. When the x multiplies that, we get x squared. In the denominator, I can also distribute the integral sign. From 0 to 2, the root 2 can come outside. So this is just the integral of x to the power half dx, then plus the integral from 0 to 2 of x dx. This x times x to the power half can be seen, same base, just add the powers. That will be x to the power 3 over 2. So we now have root 2. The first term becomes x to the power, since that the current power is 3 over 2, so it will be 3 over 2 plus 1 over that same new power, 3 over 2 plus 1. When you integrate that first part. When you integrate x squared there, we'll get x to the power 3 over 3 from 0 to 2. In the denominator, what happens there? So let's see. Something similar as well. We integrate x to the power half. So when you do that, it becomes x to the power half plus 1 over half plus 1. And then x, when you integrate that, becomes x squared over 2. So now we simplify and substitute the upper limit only, since the lower will give us zeros everywhere. You want to be very careful with skipping the lower limit. The lower limit being a 0, here it gives zeros everywhere. But for other functions like exponents, trig functions, and so on, you want to actually do substitute it as well. Because you know exponents, when raised to 0, they will not give you 0, they'll give you 1. So if you have an exponent here, don't discard the lower limit, substitute it as well. I don't have exponents here, that's why I am discarding it. So the first term becomes 2. When I add 3 over 2 plus 1, I will have 5 over 2. So this will be 2 to the power 5 over 2 over 5 over 2. Then the other term will have 2 to the power 3 over 3. In the denominator, we'll have root of 2. And then half plus 1, it will be 3 over 2. So we'll have 2 when we put 2 where there's x, so it will be 2 to the power 3 over 2. Over the same 3 over 2. Then plus, when we put 2 where there's x, we'll have 2 squared over 2. So work out this. What are you going to get? Okay, so you're saying, so is that correct? Okay, so just make sure it is exactly what we have, but let's see if it makes sense. So when we check here, clearly the centroid must be closer to this line than to the origin, because you see there is more mass this side than this side. So what we have, it should be more than the halfway point. If the halfway point is at 1, the centroid must be at a position more than 1 point, more than 1. Then what we have is 1.26. 1.26 is definitely beyond this point, so maybe somewhere here. So we can be slightly confident that probably we are right. So we can be slightly confident there. So we have got the x coordinate of the center of mass. Now we need, so remember the units, the length there is in meters, so even this coordinate will get the meter. Now we need to get y bar. Y bar, remember we said it's y tilde dm over the integral of dm. The integral of dm will not change. The same thing we had in the previous case will be what we end up having. So I might as well just get what we integrated in the previous part, since I'm still using the same vertical section and the limits are still the same, nothing is changing. So I expect the same conclusion. The only thing that will change is the numerator. The numerator will change. The dm is still the same, but what will make the numerator to change is the fact that I'm now using a y tilde. In the previous case, I used x tilde. So that is where the difference will be. So here I'll have the integral where there's y tilde. We did come up with the expression for y tilde earlier. So y tilde, we saw that y tilde would be this expression. So I'll place that expression where there's y tilde. But y tilde has to multiply dm. The expression for dm is still the same. So let's get that expression. So dm turned out to be this. Is that okay? So we now just need to simplify, then integrate. Since we are still dealing with dx, the limits are still the smallest value of x to the largest. And as you pointed out earlier, it's from 0 to 2. So constants can come out, which is the density and that 0.3, including that 2 in the denominator there. Those can come out. So I'll have the density, the 0.3, and the 2. Now remember, for me to just bring this up, it originally had the 0.3 density down here. Do you remember that? So it means that since I have taken a shortcut, I should remember that this had cancelled already, so I shouldn't have it here anymore. It cancelled with the same thing that came out from the denominator. So I can skip this. So I can even skip it from here. If I want to keep it here, it means that at this stage, I should show that those constants are round so that they get to cancel in the next step. But if you're not comfortable with this, you can show the integral first at this stage and then simplify to what the integration will reduce to in the next step. Perhaps let me do that. So I'll show the integral, and that will be so this is dm, the integral of dm. So this is where now we ended up having, so I can factor out in the numerator the half, (0.3) density. Everything else remains to be affected by the integral. So I'll have minus x plus root of 2x plus x dx. In the denominator, the density and the 0.3 will come out. And then I'll have the integral from 0 to 2 of root of 2x plus x dx. The 0.3 density will cancel out, so that now I have half from 0 to 2, and then I need to expand this. I can change the way I look at this second part and actually view it as root of 2x first minus x. And then this is also root of 2x, but now it is plus x. In the denominator, that integral, we evaluated it earlier, and it's the one that gave us this now. So now I can bring in, so that I don't have to stress about integrating again. It reduced to give us this. So evaluate the denominator. What value are you getting?
One, four, 4.667.
Okay, what's that value?
4,
4?
1, 6, 7.
Okay. So that's what we're getting from the denominator. From the numerator, we want to simplify, expand, and then integrate. So you can expand the usual way, or you can just be quick about it and observe that this and this are the same expressions with a difference of a minus between them. So because of that, I can view them as what?
Squared minus x squared.
Yes, nice. That's a difference of 2 squared. So I can view this as root of 2x squared, which will just be 2x, minus x squared. See how being able to observe such small details simplifies your work, because if you had to expand that, it was going to take you a bit of time. Integrating this now becomes straightforward. Here you have 1 over 2. The first part will be 2x squared over 2, which will just be x squared. The second part will be x to the power 3 over 3 from 0 to 2. So moving from 0 to 2, we're just going to put 2 everywhere where there is x. 2 squared will be 4. 2 to the power 3 will be 8. Over 4.6667. What are you getting here? You can even distribute that half to give us 2 minus 4 over 3. Okay. Divide to get the decimal.
One, one, four, two.
1. Is it 1?
Zero.
0 point?
1, 4,
143, like that? Okay, so just make sure everything is done correctly with your calculator. If it is, then this becomes the coordinate of the centroid. Now, it should make sense. Before you get there, let's present the values. We had 1.26 as the x coordinate. So 1.26 as the x coordinate and 0.143 meters as the y coordinate. Now here, it's possible that this was going to come out negative. If it was going to come out negative, get it as a negative coordinate. That's fine. But here it came out positive and close to the origin, to the x-axis. Let's see what that implies. So when we view the original diagram, it kind of makes sense. According to what we're seeing, that position is slightly above the x-axis, but just slightly. And it's nearer to the vertical, to x is equals to 2, than to x is equals to 0. So let's say maybe it's somewhere here. So this is approximately where it is, which makes sense. You expect this to be slightly more area or more mass compared to the one that you have at the bottom. So based on that, this makes sense. So that becomes how we solve a problem like this one. Any questions?